Hello, how are you? I want to talk about the second method of local searches. I mentioned hill climbing on the last video. This video is about something called simulated annealing. It's a rather strange place to go looking for an algorithm. What it is, it's based on work with metallurgy, metals, cooling down metals. It seems to work. I have a program that has produced some results, but it is a little bit unusual. Now, here's the way it goes. This is the algorithm. We have a problem. We have a problem that is a search problem. We have a way of scoring it, and we're looking for, let's say, the minimum or the maximum. So we're trying to minimize or maximize. So what we're going to do is we take a random guess at the solution. That's the way to start. That was the way we started the hill climbing also. Then what we do is we repeat. Oh, before I say that, we set a temperature, and I started at 100. The temperature is the reason it's called annealing, because the metal work is done by first starting with a temperature and then cooling it down, and as you cool it down, it's supposed to get better. So we pick a temperature. Now we'll repeat for a certain number of times, for n times. I chose n as 10. They said that seemed a reasonable number. What we do is generate a neighbor by whatever means we have for generating a neighbor. Then we score the neighbor. If the score is better, in my case that meant less than the score we have, we move to the neighbor, and that's where we keep going. Now here's the trick. That would be hill climbing. If the score is not better than we have, we are going to accept it in some cases. What we do is we pick a random number, between I made it between 0 and 1, and I made it but not 0. I found that it didn't really work nicely if I let the 0 in there, so I worked so it wouldn't happen. Now once we do that, we accept this neighbor if, and this gets a little complicated, if the probability that we have is less, pick a random number, let's call it PR. PR. Let's just call it P, so I have to fit it on the line. So we pick that number. Now, we accept the neighbor if P is less than, and this is the complicated equation, the exponent of the new score, the score of the neighbor, minus the score we have, that's not completed though. That's the numerator, divided by the temperature times some number. I chose 0.04. That seemed to work. What this is saying is, some of the time, we're willing to go a way that isn't optimal, that isn't the best. It helps us get away from local minima or local maxima, because we're not, we jump away. You're supposed to, this is supposed to be set up in such a way that in the beginning, it accepts maybe half of the bad ones. And as you get to the end, we reach what's called a quenching state, where it won't accept any of them. The number 0.04, I fooled around with that many times. You've got to just play with it to see what number works. Exponent, by the way, means e to the power, where e is that Euler number, 2 point something. And it's available under CMath in C++ and available also on the math in Python, I believe. Now, we just did that. So, we're ready. What I did at this point is I said, if we found a better neighbor, jump out of the loop. I wasn't going to keep going if I had found something better and possibly not have it afterwards. Now, I'm not sure that's part of the way that most people do this, but I found it worked and I decided to try it, do it. So that's our repeat. So that ends the repeat. Now we decrease the temperature. I decreased it by 1, but some of the places I've looked decreased it by 0.001. But I tried this. And we do this, I should say up here, we repeat until we reach some criteria. I chose the criteria that I got what I wanted. I reached the solution. Now that's the theory. I applied it to a problem, and I'm going to bring up my program and hope it works. So here's my program. The problem I looked at was the problem of the 8 queens, or the n queens. You're doing a 4-queen problem. I thought I'd try this problem using simulated annealing. What I did was I decided to fix it so I could have any size. I'll take it to 4 for this run, and we'll see what it does. Before I do that, I better look at what I've got here. This pot right here generates my queens. I pick a row and I pick a column for each queen. I put them on the board by using Q. If it's not Q, it's a blank. I also created 2 other arrays, row and column, and they keep track of where the n queens are. I found that was useful for what I wanted to do. Remember, our object is to put n queens on the board so none of them can take any other one. That means that they're not on the same diagonal, they're not in the same row, they're not in the same column. Then I scored it. I did it by I'll show you the function in a minute. I printed it, and then I said, well, the score hasn't reached 0. 0 would mean I got there. My score was the number of captures that could be made. So that's how I scored it. And I want 0. So now, if the score is not greater than 0, I get a neighbor, print the board, and I print out what the score is now after that. And I keep going. The print board was elementary. The score was a little complicated. What I basically did was take each queen and look at the queens it could take. The first line says, I look at the other queens. So for the first queen, I look at the other 3. Then for the second queen, I look at the other 2 below I haven't looked at yet. The third, I look at the last queen. So for the queen, I look to see if the other queens are on the same row or the same column. Those were pretty easy. Then I had to do the diagonals. It turns out that if you play around with the numbers, these work. At least it appears to me they work for determining if the other queens are on the same diagonal. And there are 2 diagonals to check. So that's my score. I return it. I don't know why I have score equals score there. I don't know what happened there. I return it. And now comes the real fun, getting a neighbor. So I decided that the easiest way to get a neighbor was to exchange 2 places on the chessboard. I didn't care if there was a queen in either of them or not. I might have been able to speed things up if I had looked for only a queen, but I just said, so what? I'll exchange 2 places. So I worked out the random numbers, did the changes. Temp C is needed for moving it back, moving the 2, exchanging the 2 places. I then recreated the row and column so I'd have them, and then I sent it to the score. Now I computed my probability, and then I said if the score is less than best, as far as I'm concerned, I'm done. So I'm going to set found better equal true. Otherwise, I'm going to check. If the probability is greater than or equal to that e to the power that I gave you before, then this meant I didn't want it. I only want it if the probability is less. So this is undoing the change I made. It's where I exchanged A with B, I'm changing A with B again, undoing it. Worked out better than trying to put up another board to play with. And I bring the temperature down. Now, the trick I didn't show you, and I'll look right now, is I do this at least either 10 times or until I found a better. So I give myself 10 tries at each of these temperatures to find a better one. Now let's see if it works for 4. So let me try running it. Here we go. There's going to be a lot of output. All right. It got down to the right answer. It said yes. What did I do? Let me see if I can bring it back. Yes. I started way back here. My choice gave me a 5. There are 2 boards there. That's why it looks so complicated. So I got a new one. And then a 3 and a 1. And then I slipped back to 3 and stayed at 3 for a while. And then I went down. I even went to 4 and 5, 4, 3, back to 4. I don't seem to be making progress. 2, 4, 3, 2. Even went up to 6. But now you can see, hopefully, that it's going to start converging. I'm now in the 2, back up again. Now I've seen a 1. I still haven't reached the convergent state. And it's certainly doing a lot of them, isn't it? But now you'll notice I'm getting the 1s, and then I hit the 0. Once I get down to the 1s, I'm where I've quenched any change, basically. The temperature's low enough to keep it from popping up. And here's my answer. You can see the 4 queens do fit on the board. So it does work with 4 queens. I have checked that. Now, before I started making this video, I tried it with 6 queens. It worked, but the rate I'm going, I don't know if it'll work again. So we'll just have to see. All right, so I'm going to go back up here, and I'm going to change this to 6. And then I'm going to run it again. I tried it without the 10, without doing 10 each, and it ran forever and forever and forever. But this worked. There's the answer, and it worked. I hesitate to try for 8, but maybe I should. So what I'm going to do is I'm going to post this program, and I'll also post the definition I gave of the algorithm, and then you'll have a chance to look at it, see what it's like. Remember, this is called a local search. It is supposed to, this and hill climbing are supposed to be better if you have a large space of continuous functions and that you want to avoid local minimums and local maximus. There's one more of these techniques. It's called genetic algorithm, and I hope to have it by tomorrow so you can see it. So long now. See you again soon.